Hey everybody, Mr. Plantt here, and I am going to go over the Semester 1 study guide with you guys today. Now this is a little bit different than other study guides we've done, just because it leaves more up to you to do. But what I mean by that is this first section, right? The majority of your study guide is this first area that says find notes for the following topics and write down what pages or page they can be found on in your notebook. And that is like 90% of your studying that you can do for this final. The questions that we've added down below, they are not completely comprehensive of the entire final, right? That means that if you just look at these questions, you're not going to study everything you need to for the final. You're going to have to know where all of these topics are in your notebook so that when the questions come up, you can find them in your notebook. It's a big belief in this class that you don't really have to memorize anything, but you do have to be able to analyze the information you have. That's why everything has been open note, everything has been, you have lots of tools at your disposal, but you got to be able to use them, know how to use them, and know how to understand them. And that starts with this section. Right, taking all of these topics and finding every page they're on. Now, everyone's page numbers will be different because everyone's notebooks are different, and so that might mean you need to organize your notebook and make sure your notebook's organized and orderly so you can find these things, but that'll be a big tool in studying itself, getting that notebook ready. By the time Monday is here, finals week, that should be done. You should have your notebook organized and ready. You should have these lists of topics filled out with their page numbers of where you can find them so that you can find whatever you need to when the final rolls around. Remember, it's a pretty big test, 60 some questions, so you're going to have to kind of be on the ball and not wasting a lot of time looking for information. Okay, with that being said, I'm going to go over the questions that we do have on here. And now keep in mind that, again, I'm not going to write out every single answer. I will talk through all the answers, but it's up to you to really fill this out. I'm just here to kind of give you some help and be a little bit of a guide to the right direction on how you should answer these. Okay, so the first question says, draw a picture of a series and parallel circuit. Include the following information for your diagram. So I'll draw the series one. All right, let's say we have some battery, and it's connected to a resistor back to the battery. Okay, now we have two different things we want to label. Okay, so we're going to do orange for the current. And now the current, if we remember, is different than the electrons. The way the electrons go, right, is they're going to go from the negative end of the battery to the positive. So if this small line is the negative end and this is the positive end, because the electrons are negative, they are going to flow around this way from the negative side of the battery up to the positive end. Pretty straightforward. The weird thing is that by convention, the current goes the other way. And there's really not a great explanation other than that's how people do it. And so current then would go from the positive end, I'm kind of running out of room to draw arrows, to the negative end. Right, so in this case, the current is clockwise, and the flow of the electrons is counterclockwise. And that's the same for parallel as well. Your circuit is just going to look a little different, but the idea is the same, that the electrons go from the negative end of the battery to the positive, and that the current goes from the positive end of the battery to the negative end. Okay, pretty straightforward. The three ways to write Ohm's law, the reason we throw this on here is that anytime we have an Ohm's law problem, so something where you have a voltage and a current and you're finding resistance or any combination of it, we need to know Ohm's law. And so my way, I always remember VER, or V equals IR. So V equals I times R, or voltage equals current times resistance, and then I can rearrange from there. So you'll kind of have to go through and do the two other equations, the I equals V over R, because we divide this R to the other side, or R equals V over I when we divide the I to the other side. And that gives you your three basic equations for Ohm's law, so that anytime one of those problems comes up, depending on what is given to you, So say you have current and voltage and you're looking for resistance, you don't have to worry about the equation. You have the version that you need right away, and you can just plug in your numbers and solve. Okay, stretching back a little bit to the beginning of the semester, it says fill out the following table. And so it has our subatomic particles. So if we remember correctly, that is the proton, the neutron, and the electron. Okay, and so the proton, its symbol is P plus, the neutron is an N0, and the electron is an E minus. And that plus, 0, and minus has everything to do with the electric charge, which we're going to hop over to that column. The proton has a positive 1 charge, the neutron has a 0 charge, and the electron has a negative 1 charge. And so this connection kind of between this number and that symbol is how I remember each subatomic particles symbol. Location-wise, the protons and the neutrons form the nucleus of the atom. So they are in the center, in the nucleus. And then you have the electrons flying around in the electron clouds, or the orbitals. Electron cloud. Can I squeeze it in? Yeah. The electron cloud. And that's because the electrons are the things that can move around. We saw that when we started talking about electricity and the fact that it's only electrons that can move from one object to the other. So really we can only change negative charge. We can't add positive charge to things, but we can take away negative charge, effectively making things positive. Okay. Atomic mass. This one's nice and easy because we use something called AMU, or atomic mass units. And in this case, the proton has a mass of 1, the neutron has a mass of 1, and the electron is about 0. It's so small that we never really consider it. Okay. And last but not least is how do we know how many there are? This has a lot to do with our atom identification. Remember those tables we filled out where it was the protons, the neutrons, the mass number, the atomic mass, or atomic number, and all of those things. That all stems from this. So the proton, remember, is always the atomic number. The neutron is, we can tell how many neutrons there are by, let's see, mass number minus atomic number. Okay, and then how many electrons there are. And this one was the one where we said it's the same as the protons if charge equals 0. So if we have a neutral charge, then the proton number is the same as the electron number. If not, then you do your it's kind of protons minus electrons equals your charge, and you can kind of fill in whatever pieces you need to find the missing piece. All right, moving on. The question, what type of materials are good conductors? So to know this, we got to remember a conductor is, and we have two types, right? We had heat and electricity. So when we talk about heat and electricity, a conductor is always something that easily allows heat or electricity to go through it. And so a lot of times this is metals, in both heat and electricity's case. A metal lets heat go through it easily, and it lets electricity go through easily. So then the opposite side of that is our insulators, right? And these are the things that stop the heat going through easily. So things like rubber and wood and air, they're all insulators. Usually anything with air pockets is a good insulator. And so you can think about it as like an insulator has, we have 3 lines of heat, and then we have some sort of insulator, and only 1 line of heat gets through, right? Whereas for a conductor, you have 3 lines of heat, and you have some metal, and pretty much 3 lines of heat get through. It lets all that heat pass right through it. Okay, and so we need to be thinking about things that are good insulators and conductors because they will affect things like resistance, right? If you have a better conductor, you will have less resistance. So that kind of thinking is a really good example of how you should be using the study guide. That question alone, just answering metals are good conductors, rubber and things with air are good insulators, isn't where your understanding should stop. That's just the beginning. Okay, so we should be able to know, okay, now that I know what a good conductor and a good insulator is, what does that mean? Right? So does that mean the resistance will go up or down? Does that mean that my heat will be able to flow through conduction or convection, or how just really any sort of process will operate because of what's a good conductor and insulator? It's that application piece. Moving on. What is the difference between a chemical and physical property and a chemical and physical change? Well, the big thing is when we think about chemical or physical anything, a chemical change, right? So if we do chemical and physical change, a chemical change makes a new substance. Right? Physical change does not. So if we have a new substance at the end, a new molecular structure, it'll be a chemical change. Chemical and physical property is along the same things, right? A physical property is something that can be measured without changing the substance, and a chemical property, to really measure it, you have to change the substance. So, for example, a physical property might be malleability. Right? You can bend and push and jab the substance without changing it. But a chemical property might be combustibility. So you have to light it on fire, and the act of burning it is going to destroy it and turn it into a new substance. Now, the reason we bring this up is throughout the year we've had a lot of confusion between properties and change. So you really have to be specific as to what is a chemical and physical property. So what's something we can measure about the substance, and a chemical or physical change, which is an action that causes it to become something new. It's a very fine line that is the difference between the two, but it's still very important. Okay, we're hopping all around with these questions, but that's okay because we have a lot of stuff to go over. So, chemical equations, balancing chemical equations. In general, there are some easy ones which you can kind of just look at. But the general steps, remember, are 1, you have to count your atoms. If we don't know how many of each element there are in our chemical equation, it's going to be hard to balance them. So we have to count our atoms. Okay. 2, we want to identify types of elements. And what I mean by that is the metals and the nonmetals. So metals and nonmetals, especially for the more complicated balancing equations. This is very, very important, is being able to identify which ones are metals or nonmetals, because step 3 is how you solve it, and that is you do your metals, then your nonmetals, then hydrogen, and then oxygen. And if you do the hard ones in this order, more often than not, you never have to balance hydrogen and oxygen, as long as you're remembering every time you do something, you go back, and if a metal's unbalanced, you go right back to that metal and balance it again. Okay, so that begs the question, what is a metal and what is a nonmetal? Well, luckily for us, there's a really easy way to tell this, right? If we have our periodic table of Mr. Plantt's horrible drawing, right? We have an easy way of telling which ones are the metals and nonmetals. The first thing I'm going to point out is this guy up in the top left. Hydrogen is a nonmetal, because that's the only break in our pattern, nonmetal. Okay, all the other ones, we kind of have this zigzag line. I call it like the stair step of metalness, where everything on the left is a metal and everything on the right is a nonmetal. Okay, so as long as you remember left side of the line metals, right side of the line nonmetals, and that hydrogen's a nonmetal, you will be all right. Okay, Types of bonds, because that kind of ties into metals and nonmetals. An ionic bond is something where we're transferring electrons from one object to another. So the big idea is the transfer of electrons, and that might be something like, let's say sodium, right? NaCl. And so the big characteristics here is that sodium is a metal and chlorine is a nonmetal. So an ionic bond is always between a metal and a nonmetal. And if we remember kind of our pictures, right? Sodium has, let's look at my periodic table, one outer electron, and chlorine has 7. So it is going to sodium, the metal, is going to give up its electron to chlorine, and you're going to get, right, an ionic bond that is Na loses electron plus Cl minus. That's the big idea of an ionic bond and some of the applications we used it in. Another way where just the definition is not what we need to know. The definition is the starting, the foundation of what we need to know. But then we need to be able to apply it to like these electron dot structures, or saying a metal and a nonmetal combine to make ionic bonds. So it's not just enough to have this very definition-based understanding. Right? Chemistry and physics is hard stuff because of the application. You take what you know and you have to apply it to situations. Okay, covalent bond is 2 nonmetals, right? And the one I always like to use is water, which we talked about. Water's kind of weird because it's a special type of covalent bond called a polar covalent bond. But really, if I draw a picture of oxygen, which has 6 electrons, I can imagine that the hydrogen, oops, that's not the symbol I want to use, the hydrogen, which has 1 electron each, goes so that this hydrogen shares 1 with oxygen, this hydrogen shares an electron with oxygen, and the oxygen shares both of the electrons with hydrogen. So that sharing, the sharing of electrons, is the real key idea of a covalent bond. Yeah, it's a bond between 2 nonmetals, but really the defining characteristic is the sharing of electrons. Right? Their electronegativities are about the same, so that we know that they're sharing the electrons. There's not that big difference in who wants the electrons, which we'll get to in just a little bit. Okay, big concept that has a lot of application. How can you identify an ion, an isotope, and an atom? So this has to do with our 3 subatomic particles. We can tell the type of atom by the number of protons. You can tell if something's an isotope by the number of neutrons. And you can tell something's an ion by the number of electrons. Okay, and so really we identify an ion because it has a different number of electrons than protons. Either more or less is kind of irrelevant. It just has to be either a positive or a negative ion. Positive called the cation, negative called the anion. And so that's how we find an ion, by the number of electrons as compared to the number of protons. An isotope is when the number of neutrons is different than the average number. So if we think about the mass number on our periodic table, we usually get things like, for carbon, 12.011. Well, we can't have 0.011 of an subatomic particle, right? It's not like you have 6 protons and 6.011 neutrons. It's an average. It's saying the most common number for neutrons in carbon is a little bit over 6. And so if you have a sample of carbon that's carbon 14, well, that would be 6 protons and 8 neutrons. So that would be an isotope of the carbon atom. And the way we know it's a carbon atom is by the number of protons. And that's the easy one, right? That if it's 6, it's always carbon. If it goes up to 7, now it's nitrogen. Right? It's just the big number on the top of the letters in our periodic table, and it's always, always, always telling us the type of atom that we have. Okay, I kind of hinted at this next question a little bit in my previous explanation. What does a high electronegativity tell you about an element? Well, electronegativity is kind of how much an element wants an electron. How much an element... And I put wants in quotations because it doesn't want anything. It's an inanimate object. But how much an element wants electrons. So if it has a really high electronegativity, it will have, it'll really, really want electrons. And if it has a really low one, it doesn't want electrons. And so we can use this idea of electronegativity to figure out ionic and covalent bonds again. Right? That if you have a really big difference of electronegativity, one atom wants electrons way more than the other, then it's going to steal the one that wants the electrons more is going to steal the electron, and you'll have the transfer of electrons or an ionic bond. If they're about the same, they're going to both tug on the electron and they're going to share it, which is a covalent bond. Okay? Pretty straightforward. Back to some circuits. We're just hopping all around this type of stuff. Draw what a battery, resistor, and light bulb look like on a schematic diagram. Well, there's some different pictures sometimes. Like we had a worksheet where a battery looked like this, but that's not usually normal. Normally, a battery is just a big line on the positive side and a small line on the negative side. A resistor is just some zigzag lines. And a light bulb is, this is the one that changes the most, but it's normally a circle with some stuff inside of it, some squiggles. Some people do other things, but more often than not, it's pretty obvious to tell if it's a light bulb or not. Okay, how do you calculate total resistance in a series circuit? This was really, really important because we were doing a lot of these, and if the math is easy enough that if I'm going to give you math on the test, more often than not, it's going to be a series circuit. So if we have something like this, right, let's do three resistors in series because they're in a straight line, one loop, right? And let's say this is 6 ohms, 2 ohms, and 4 ohms. And remember, the symbol for ohm is this omega. To find our total resistance in series, we would just add them up. 6 plus 2 plus 4 is 12 ohms. But this is only for series. Right? Only. It is not for any other type of circuit but series circuits. Okay. Which brings us up to the voltage in a series circuit with multiple batteries. Well, if they are facing the same direction, like this, we just add them together. Right? If these were 2 and 2, 2 plus 2, our V total would be 4 volts. But the thing to remember is that if they're facing opposite directions, then they are pushing in opposite ways. So if this is 8 volts and this is 6, our total voltage would actually be 8 minus 6, or 2 volts, because they're facing in opposite directions, which means they're pushing in opposite directions. Not so good. Moving on to parallel, that is the one that gets a little more complicated, because we have that crazy equation that 1 over R total equals like 1 over R1 plus 1 over R2 plus 1 over R3, dot, 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 for as many resistors as you have. But we're never going to make you do that math because it's a little bit messy and takes too much time. So the big thing we want to remember is that in parallel, right, when we have multiple branches, multiple pathways for electricity to follow, our total resistance is going to be less than the smallest resistor. So if the smallest resistor is 4, then our total resistance in parallel is going to be less than 4. Okay, and we've asked that on a couple quizzes and a couple worksheets, right? Give the range, give an estimate, try to predict what the total resistance would be, and what we're looking for is some sort of indication that it's smaller than the smallest resistor. Okay, one last thing, and then just a couple general tips and tricks. But how does the movement of electrons produce light? This is a big one when we talked about the spectrum of light, and it's going to come up again, so be ready for it. When we talk about light spectrum, and we're talking about how does electrons produce light, we have to remember a little bit about the atom. So let's say here's our nucleus, and it has some sort of combination of protons and neutrons inside of it. We're not going to worry about it. What we're going to worry about is outside the nucleus in these orbitals. All right, let's just worry about these first two. And let's say we have an electron that is right here. So, to get up to this next orbital, this electron needs to gain energy. So it absorbs energy from some sort of event. Why that happens, well, not really worry about too much right now, but it gets hit by something, it absorbs energy in some sort of way, and it pops out to this higher energy level. And then one of the craziest things happens that we still don't have a great explanation for, is it'll spontaneously lose that energy. So then this goes back down. Okay, this is when it gains energy. When it drops back down, right, when that electron, it loses energy and kind of falls to a lower orbital, that lost energy is released as light. So the lost energy, sorry about my handwriting, is released as light. And we can even kind of make some judgment calls about the color of light because of the amount of energy lost, which is pretty cool. You might have to go back and look at some of the stuff from our first unit to kind of shake your memory about that sort of action of how we can tell from the frequencies of light, which light has the most energy, how we can tell what the color of light is. But the big concept here is that as those electrons lose energy and drop down orbitals at random, we don't really know why, they just lose that energy, they release that energy as light, right? Because the conservation of energy, let's not forget that. Let's add that, right? Conservation of energy, and that says energy cannot be created or destroyed, it only changes forms. So as that electron is dropping down and losing energy, that energy has to go somewhere, and in this case it goes to light, and it gets released light, and that's how we get light. It's pretty nice. It only changes form. Okay, we're going to call it there, guys, but hopefully this gives you a start. Remember, this alone is not enough. You cannot rely on just these questions to do amazing on the test, right? Maybe just the questions will get you, I don't know, 50-60% of the way there, and this whole section, right, knowing where to find the information will help you the rest of the way. But the only way to really get a good grade, a B or an A, is to understand what that information means. So after you find the pages on it, go back through your notes, make quiz questions, go back through our worksheets and the quizzes we had, and quiz yourself, write your own quiz questions, quiz a partner, test vocabulary, so that you really understand the content, because without that, a lot of these questions will get hard. You have to be able to understand and apply what you know. Okay, it's going to take studying and it's going to take some hard work, but if you put in the time, it'll be worth it. Alright guys, we're going to call it there then. Good luck as you start studying. Make sure to stay in contact with me and Mr. Armstrong so that we can answer all of your questions. You can always message us on a Remind, and we're more than willing to help you out as soon as we can. You can always get on Schoology or our class calendar and go look at some of the old content we've covered and how long we've spent on it. And yeah, have fun, guys, and I will see you in class. See you later.